This is the part 6 of heterocyclic compounds. In this sixth part, let us see the chemical reactions of pyridine. As we have seen already, pyridine undergoes both electrophilic as well as nucleophilic substitution reactions. There is another set of reactions in which pyridine acts as a base or nucleophile. That means three types of reactions are shown by pyridine, that is electrophilic substitution reaction, nucleophilic substitution reaction, and which the reactions in which it acts at base or nucleophile. These reactions involve nitrogen directly. That means these reactions are due to the presence of nitrogen in pyridine. These are due to its unshared pair of electron on nitrogen. And specifically, these unshared or lone pair on nitrogen is responsible for all these reactions. So let us see one by one how basic characters of pyridine are shown. Pyridine is a base and its pKb value 8.8, that it is comparable with aniline. The pKb values of both are comparable. Pyridine is a stronger base than pyrrole. We know this is the structure of pyrrole, and pyridine is a stronger base, but a weaker base than aliphatic tertiary amines. So basic characters of pyridine is due to availability of lone pairs of electron on nitrogen. The lone pairs on nitrogen in case of pyridine, they are not involved in aromaticity. So the lone pair of electron are not involved in formation of aromatic sextate. That means they are free, or the this lone pair is readily available for sharing with acid, and this is the reason why pyridine acts as stronger base when compared with pyrrole. In contrast, the electron pair on nitrogen in pyrrole involves the formation of aromatic sextate. So these electrons are engaged, they are involved in aromatic sextate. That means 1, 2, 3, 4, 5, 6. These 6 electrons are engaged in aromatic delocalization or aromatic sextate, and they are not available with nitrogen. So it is weak base. Pyrrole is weak base. But this is not case with pyridine. In case of pyridine, 1, 2, 3, 4, and 5, 6, 6 pi electrons are already there for the formation of aromatic sextate, and these 6 electrons comes from 3 pi bonds in the ring, and this lone pair of electron is readily available for showing basic characters. Hence, pyridine is stronger base as compared with pyrrole. Pyridine behaves as monoacidic tertiary base. Tertiary nitrogen is there, so it is tertiary, and monoacidic. That means one acid molecule is sufficient to form salt with pyridine. The following reaction explain the basic nature of pyridine. And the first reaction is pyridine on reaction with HCl forms pyridine hydrochloride salt, or pyridine reacts with any acid to form corresponding salt. The reaction, specific reaction is pyridine upon reaction with HCl forms pyridine hydrochloride salt. It is also known as pyridinium chloride. So here the Cl minus is coordinated with this pyridinium cation. Then next reaction is pyridine reacts with methyl iodide to form N-methyl pyridinium iodide. Pyridine on reaction with methyl iodide forms N-methyl pyridinium iodide. Here nitrogen forms bond with methyl. It becomes electron deficient or positively charged, and iodine I minus coordinates with this cation. Then let us see the second part of reactions, that is electrophilic substitution reactions. Pyridine behaves as highly deactivated aromatic nucleus. That means it is not readily showing electrophilic substitution reactions. But if it has been pushed, if more energy is given, if it is activated, then it can show electrophilic substitution reactions, such as nitrobenzene towards these electrophilic substitution reaction, and it undergoes nitration, sulfonation, and halogenation only under vigorous conditions. Elevated or higher energy conditions are required for this nitration, sulfonation, and halogenation. On the other hand, it does not undergo Friedel-Crafts reaction. Friedel-Crafts alkylation or acylation, these reactions are not shown by pyridine. The low reactivity of pyridine towards electrophilic substitution is due to these reasons. And the first reason is it is more electronegative nitrogen which is responsible for its decreased electron density over the ring. And as electron density decreases over the ring, the electrophilic substitution reactions are not shown by that molecule. As electrophile attracts towards electrons. So if more electron density is there, electrophile easily attract towards molecule and it will show readily electrophilic substitution reactions. But in case of pyridine, nitrogen is more electronegative. It pulls electron from the ring towards itself, and this aromatic 6 state is not that much free due to minus I effect of nitrogen. Hence, it deactivates this ring towards electrophilic substitution reactions. This is the first reason. And second reason is most of the electrophilic substitution reactions are carried out in acidic condition. In acidic condition. And we know when pyridine reacts with acid, it forms pyridinium cation that we have seen already. Under acidic condition, pyridine forms pyridinium cation with positive charge at nitrogen, like this. And thus nitrogen decrease the electron density more effectively on the ring. As it becomes positively charged, it pulls this aromatic sextate towards itself more effectively. That means it decreases the electron density over the ring more effectively, and it deactivates the ring towards electrophilic substitution reactions. Also, pyridinium cation, as it is positively charged, it repels the electrophile which is positively charged. This is the reason why pyridine shows deactivated, or it is not showing readily electrophilic substitution reactions. So if at all it is showing nitration, sulfonation and halogenation reactions, though with deactivated ring, what is the orientation where the incoming electrophile will attack? It will attach to which carbon? This is known as orientation of the electrophilic substitution reaction. So when we see different possibilities, attack at position 2, these are the position. Nitrogen takes one position, 2, 3, 4, 5 and 6. So attack at position 2 gives 3 resonating structures. Attack at position 3 also gives 3 resonating structures, and attack at position 4 also gives 3 resonating structures. But when we see attack at position 2 and 4, we come to know, we observe that there is positive charge on nitrogen when delocalization takes place, or when this sigma complex stabilizes by delocalization or its canonical structures. Similar is the case with attack at position 4. There is positive charge on nitrogen, and being more electronegative, nitrogen cannot afford the positive charge. It becomes more unstable, and we know the more unstable product, or the more unstable canonical structure, is more difficult to form, and more stable canonical structure is more easy to form. So in case of attack at position 3, we observe the positive charge do not come on nitrogen in any of the canonical structures, any of the delocalizing structures. So this attack at position 3 is more preferable. It is more energetically preferable, and we observe the reaction of pyridine, that electrophile attaches at position 3, and this is the product generally we get when electrophilic substitution reaction occur in pyridine. So attack at position 3 or beta position, nitrogen 1 just next to the nitrogen, that is alpha carbon, and next to alpha beta. So beta attack is more preferable in case of pyridine when electrophilic substitution reactions are considered. So what is the mechanism of this electrophilic substitution reactions? In brief, the mechanism of electrophilic substitution reaction involve following steps, and the step 1 is attack of electrophile at position 3. to form carbocation intermediate, and that is known as sigma complex. So here these electrons will attack on positively charged electrophile, and we get this sigma complex. Intermediate sigma complex is resonance stabilized, and it is less stable as it loses its aromatic character. This is non-aromatic, as conjugation breaks here. There is no alternate single and double bonds. In second state, the proton has been lost from the carbon where the electrophile is attached. Remember, hydrogen should be lost from that carbon only where electrophile is attached. And when hydrogen is lost, these electrons, bonded electron forms double bond here in this way, and it regains its aromatic character or aromaticity. And as it become aromatic, it is more stable. So this is a fast step, and first one is slow or rate determining step. This is fast step, and it involves regaining of the aromatic characters of pyridine. So there are some examples of electrophilic substitution reaction. First one is nitration, where pyridine reacts with potassium nitrate and concentrated sulfuric acid at 300 degrees Celsius. We give 3-nitropyridine. Remember, every incoming electrophile will attach at 3 position. If one of the beta position or 3 position is blocked, then second electrophile will go to second beta position. Sulfonation. Pyridine on sulfonation gives 3 pyridine 3-sulfonic acid, and sulfonation is carried out by heating pyridine with oleum. This oleum is dense H2SO4 or concentrated sulfuric acid containing SO3 at 300 degrees Celsius in presence of HgSO4. It gives pyridine 3-sulfonic acid. Then bromination, pyridine on bromination with Br2 at 300 degrees Celsius forms 3-bromopyridine and 3,5-dibromopyridine. So monobromination and dibromination also takes place in case of bromination reaction. Thank you.